In this module, we're going to move from the kind of static world of compounds and elements into the world of chemical and physical change. And this is, of course, where things get really exciting. We're going from just a lump of stuff kind of just sitting there that we want to describe to thinking about how substances combine with each other to make new substances, and primarily here, how we represent that and think about that on the submicroscopic level. So, in this first video, we're going to start by distinguishing between what we call a chemical change and a physical change, and be able to recognize the difference not just in terms of the properties of each type of change, but also in equations containing chemical formulas, what we'll call chemical equations that might represent either a chemical change or physical change. It's a little bit confusing. The equations themselves are called chemical because chemicals appear in them, although they may represent either chemical change or physical change. And then we're going to talk about interpreting chemical equations so that we can visualize chemical reactions or physical changes, and this is building on our prior submicroscopic understanding. We'll use things like our typical picture of solids, liquids, and gases at the submicroscopic level to start visualizing how chemical reactions work at the submicroscopic level. So we're going to start with physical and chemical changes. What are physical and chemical changes? Well, a physical change is one that alters the state or appearance of matter, but does not affect the chemical composition of that matter. State and appearance, here we're referring to physical properties. So physical changes are associated with physical properties. For example, melting wax, you see in the figure here, this is a physical change. The wax is just going from a solid state to a liquid state. Likewise, with this condensation of water on the pot on the right, this is just a physical change. The water molecules are H2O throughout the process. They're just going from the gaseous state to the liquid state. Chemical changes alter the chemical structure of a substance. This means that chemical bonds are broken and formed, and on a more pedestrian level, chemical formulas change. So for example, when iron reacts with oxygen to form rust, rust is a chemically different compound from metallic iron and oxygen in the air. So this is a chemical change. The iron and oxygen are forming bonds to form the iron oxide product. Chromium, by contrast, does not react with oxygen, and this is an example of a chemical property. There's no change occurring, but the lack of reaction of oxygen is a chemical property, and here, as above with physical changes, chemical changes are associated with chemical properties, like whether a metal rusts or not. We represent changes in chemical substances using chemical equations, and these contain chemical formulas and usually phase designators. I like to use phase designators whenever I can because they help me visualize what's happening in the reaction on the submicroscopic level. And we're representing the state of a chemical system before and after some change. So we'll have some substances on the left side, substances on the right side, and an arrow between them. And to the left of the arrow, we'll have a set of chemical formulas called the reactants in a chemical change. And on the right-hand side, we'll have a set of chemical substances called the products. And the idea here is that we start from an initial state in which we have reactant substances. They react with each other, and at the end of the change, we have a new set of substances that we call the products. Although these kinds of equations are used to represent physical changes as well, and physical changes only involve a change in phase designator, not the chemical formulas on either side. So we might see, for example, liquid H2O on the left-hand side and gaseous H2O on the right-hand side. H2O and H2O is still the same chemical substance, right? It's all water, but what we're seeing here is a change in phase or state from liquid to gas. That's a physical change. Now, in chemical changes, molecules may combine with each other in different number ratios. And we use a number before each chemical formula to indicate the number of molecules or formula units reacting per reaction occurrence, and this is known as a stoichiometric coefficient. It tells us how many of each species is involved in the chemical change. As I just mentioned, these coefficients reflect the number ratios in which formula units combine in a chemical reaction. And these coefficients can be scaled to any magnitude, just like the amounts in a recipe. So I want to use a metaphor to kind of drive this home, the metaphor of making pancakes. Say it took us 1 cup of mix, 0.75 cups of milk, and 1 egg to make 8 pancakes. This recipe is very reminiscent of a chemical equation, right? On the left, we have the reactants, our ingredients, and on the right, we have our products, the 8 pancakes, right? Before each substance that we combine on the ingredient side or what we get on the product or output side, we have an amount. And here it's not a number count of things, but it gets the point across that these are like the stoichiometric coefficients in a chemical equation. They tell us how much of each ingredient we need to use and how much of the product pancake we get out. These ratios of ingredients apply at any scale, and if you've ever cooked, especially for a large group of people, you know how this works. If you need to scale a recipe, we can just multiply each of these amounts by any scale factor to maintain the ratios while still getting the right combination of ingredients to make pancakes that taste good, have the right texture, etc. So for example, we could double everything, go up to 2 cups of mix, 1.5 cups of milk, and 2 eggs. We'd get 16 pancakes. It's still the same fundamental process. The same thing happens with chemical equations. As long as the number ratios of the different species are maintained, we can apply a chemical equation at any scale and multiply all the stoichiometric coefficients by any scaling factor. We'll see how this works in detail with a chemical example very shortly. This slide shows us some examples of chemical equations that represent physical or chemical changes. The first shows the evaporation of water. And throughout this discussion, I want to encourage you to think submicroscopically here. Try to visualize what the reactants look like. Even if you don't know much about how molecular structures are put together, something we'll touch on in a future module, you can still think of each molecule as a kind of teeny tiny sphere, right? And use our typical models of solids, liquids, and gases to think about each phase submicroscopically. So the liquid phase, for example, looks like a bunch of molecules relatively close together, but kind of randomly oriented, flowing over one another, right? And on the right, we have H2O in the gaseous state, and now the molecules are much farther apart from one another, moving much faster, etc. This is evaporation, and it's a physical change. Notice there's been no change in the chemical formula. H2O to H2O, that's a physical change. The combustion of butane is shown next, and this is a chemical change, and we can tell that because there are completely new species on the right-hand side of the chemical equation. Butane, C4H10, and oxygen, O2, are converted into CO2, carbon dioxide, and water. And the stoichiometric coefficients here, by the way, no coefficient implies a 1. 1, 6.5, 4, and 5. I'll just draw your attention to the 6.5. This may seem odd if you're thinking on the submicroscopic level. How can I have 6.5 molecules of oxygen? Half an O2 molecule is just one oxygen atom, and that's not the same as an O2 molecule. So how is it possible to have 6.5 molecules of O2? Well, at that scale, it's not really. But keep in mind, we can apply this recipe. Every chemical equation is essentially a recipe at any scale. So we can multiply all those coefficients by any scaling factor to represent the same chemical equation just at a different scale. So if I wasn't comfortable with the 6.5 O2 and I wanted whole numbers everywhere, I could multiply all these coefficients by 2 and I'd arrive at the next equation on the slide. 2 C4H10s now, 13 O2s, yielding 8 CO2s and 10 H2Os. And this equation is essentially equivalent to the more reduced version that we see right here. We can also multiply all the coefficients by Avogadro's number. And in doing this, what we've done is gone from the scale of a single molecule of butane, one molecule of C4H10, to a mole of C4H10, and the corresponding numbers of moles of all the other reactants and products. So this reaction also works at the scale of 1 mole of C4H10, reacts with 6.5 moles of O2 to yield 4 moles of CO2 and 5 moles of H2O. And we'll often think about this scale macroscopically, right? If we're running the reaction on a macroscopic scale, I'm not going to have just 1 molecule of butane, right? I'm going to have an amount of butane that is much closer to 1 mole. So it's helpful to think on the molar scale. And again, if we're not comfortable with 6.5 moles of O2, which is a perfectly valid number of moles, but if we're not comfortable with that, we can multiply by 2 again and get the equivalent chemical equation at the bottom of this slide with 2 moles of butane and the corresponding amounts of everything else instead of just the 1 mole. So chemical equations apply at any scale, just like the pancake recipe. Depending on the amount I want to make or the amount of stuff that I have on the reactant side, I can think of this chemical equation as occurring at absolutely any scale, and these number ratios that are built into this simplest version of the equation apply at any scale. A couple of lingering questions about chemical equations. So far, we've just been provided with chemical equations. For example, I just told you that when butane and oxygen come into contact and there's a spark, the products are carbon dioxide and water. But is there a way to predict that, especially in cases in which we can envision the substances reacting with each other in more than one way? How can we predict the outcome? And what about a chemical equation makes it physically plausible in the first place? So part of this prediction process, this sort of harkens back to the first question, part of this prediction process is verifying that a reaction is actually physically possible. When I write down a set of reactants and a set of products, what natural laws constrain the possibilities for that being physically allowable? Or is anything possible? Do we want to approach chemical equations from the perspective that absolutely anything is possible? As you might suspect, that's not entirely true, and the laws of thermodynamics, which we'll start to touch on in a future module, constrain chemical reactions, constrain the space, we might say, of physically possible chemical processes.